So we're going to be doing Fourier analysis typically with some type of time varying signal. Again, it could be other, more generally, it could just be any, signal that is varying or even static. It doesn't matter. That's kind of the beauty. Fourier analysis is extremely general, but for the most part, we're going to be dealing with time varying signals and we're going to be converting it to the frequency space. So you've probably seen this before. Probably in vibrations. So a function, we're going to classify it as harmonic if we meet the following conditions. So if we take the derivative or the second derivative of our function, y of t will be equal to y of t minus some constant. So you can prove that both basically sinusoidal functions are harmonic functions. 2x, however, is not harmonic, right? We can prove that and see that that is indeed the case. Additionally, when you're dealing with sinusoidal signals, you'll typically see it in terms of circular frequencies. What are those units? Radians per second. Cyclical frequencies, hertz, or 1 per second. So really, really important how we can relate the two of these. Be sure that you kind of, you know what is essentially in that signal. When you're dealing with a typical sine, it's going to be some omega t, right? So radians per second. So be sure, again, however, most of the time we really want to work with things in hertz instead of circular frequency. So just be clear about that as we're working through problems. And there's going to be a lot of problems where you're going to see inverse, and because people do, unfortunately, kind of switch those or report different numbers, and we want to make sure that we can be able to work with those. So let's go ahead and let's figure out how we want to do some of these analysis. One of the key things, and you kind of see me plotting what's called basically, this is a Fourier spectrum. And this C of n is basically the harmonic coefficients. So the key idea is we are going to take that time varying signal and we are going to approximate that time varying signal with a Fourier series that has basically an infinite number of harmonic coefficients that we'll rewrite as basically a sum of sines and cosines. And then we're going to take those harmonic coefficients and we're going to plot the magnitude of the harmonic coefficients to figure out our frequency signal. So basically what frequency dominates based on the magnitude of those coefficients. So that's kind of the key and quintessential idea of basically a continuous Fourier transform. And a continuous Fourier transform is when we know the shape of our y of t function. So we know what this function is, and we can calculate that, and we can approximate it. So this is effectively how we're going to calculate those harmonic coefficients. This is a very general function. You should be aware that there's always some slight differences, at least numerically, when you're doing in calculating harmonic coefficients. If you're using MATLAB, if you're using Mathematica's kind of image periodogram, or actually just the simple Fourier series. But I think this is the most kind of robust, and it's the one that's most, I think, numerically accurate. So you'll be able to find like similar maximum frequencies, fundamental frequencies, dominant frequencies, but I think this approach is probably the most thorough and rigorous approach. So a sub n is the number of your harmonic coefficients, so 1, 2, 3, 4, 5, all the way to infinity. And you can go ahead and you can start to kind of calculate those things. Remember, you have omega equals 2 pi f. Your fundamental frequency, and this is very important, there's a couple definitions here that are important, is 1 over t, which is your period. And you can see how you can relate omega and delta f. And what we can do is we can rewrite, this is a general equation, but again, because we live typically in a cyclical frequency world, this is the one that we're typically going to work with. So this is a very important equation. And then we're going to calculate our harmonic coefficients as so. So this is really the key concept, the key idea. So we're going to take 2 over the period. You're going to define the period, even if my signal is not periodic. So if I have something that looks like just this, and then it stops, my period is this, right? However, if my period, my signal is periodic, then my period is going to be, something like this. So you can always work, I think that's another common misconception with Fourier transforms is that, my signal has to be periodic in some way. No, that's not true at all. So let's go ahead and let's work some examples. So hip to b square. I have a square wave. It goes from 10 to 20, back 10 to 20, 10 to 20, et cetera, et cetera. One of the first things I can see here, this is going from 0 to pi, 0 to 2 pi. So my period is going to be 2 pi t. So now my fundamental frequency, or my lowest frequency, is 1 over t. So you already found your fundamental frequency here, and that's beautiful. Additionally, if I'm going to continuous Fourier transform, depending on my number of harmonics, and this is delta f, n times delta f, that is going to be my max frequency. So whatever my largest value of n that I choose, that's your maximum frequency. Dominant frequency, that's where we have to kind of calculate everything here. So let's go ahead and let's jump into Mathematica. And we're going to go and actually, I'm going to try to pull, let's try to minimize this a little bit. So let's see how we're going to work with this. Because it's like a piecewise function, we're going to actually have to do 2 steps for our integration. Let me just move this over a little bit more. Let me snap it over here. Great. Okay, so you see we have our function here. Now we can go ahead and do 2 pi. Now a naught is an interesting, so our 0th order coefficient. What is cosine of 0? Because we're just substituting in that n. Cosine of 0 is what? 1. What about sine of 0? X. This is really important. B of 0 is always 0. A of 0 is just basically we're removing essentially all the cosine information. So my 0th order harmonic, and you can kind of question, like, is the 0th order harmonic important? Yes, when you're kind of doing your Fourier series approximation. In your analysis, because it's a 0th order frequency, I would say it's probably not as critical. A of n, you can just see again, so I'm integrating this over this bound, this over this bound. You see we're just going to leave n here because we're going to plug that in. So we're integrating that. My b sub n, we can get that as well. And you can now go ahead and you can see plugging in for a sub n, all of my, actually in this instance, all of my harmonics for a are 0. So my c sub n, which is this, I'm only going to plot it. Basically, it's only going to come from b of n. So I can go ahead and I can plot you can see here, I'm plotting my frequency, fundamental frequency times I, because it's just I times those number of harmonics. And I'm just kind of increasing my number of harmonics here. So we can see, and remember this is it's not the 0th order. So we can see this is our frequency spectrum. So what's our dominant frequency? Our dominant frequency here is actually our fundamental frequency as well. So 0.16, or basically 1 over t. Our maximum frequency would just be, in a continuous Fourier transform, how many number of harmonics we have. So it's just going to be 10 times that delta f. So that's kind of fixed there. So that's great. And that's a very useful. And so you found fundamental frequency, lowest frequency, all of that stuff, which is fantastic. But let's say you wanted to like approximate that signal for some reason. Let's say I wanted to, let's say, I have some function and I want to approximate it because I want to put it into a function generator, et cetera, for some reason or another. What you would do is you would take now those harmonic coefficients and you would plug them into this expression here. And remember, omega equals 2 pi. You can have delta f when you're plugging into this expression here. And so it's just going to be a naught over 2. And then I'm just going to sum. So I'm going to sum those equations. You can see sum in Mathematica is total. And I'm just going to plot it over here. And I'm just going to go, and I'm going to do it for, how many coefficients? I'm going to do it for 10 coefficients. So actually, I'm going to zoom out here. Actually, so I'm going to approximate my square wave. I'm going to go to 75. I'm going to approximate my square wave. And you see I've got some, I need to apply my sig. I'm overlaying it essentially on this plot here. So I need to shift enter. There we go. So looks pretty good. So this is with 10 harmonics. If I do 5 harmonics here, the approximation gets worse. If I do 500, now it's looking nice. So you can adjust essentially, again, as you include more harmonics, you approximate the signal essentially closer and closer and closer. How many harmonics do you need to get good enough signal? Depends on the problem. So that's it. That essentially is your Fourier analysis. We can do the same thing, and you can kind of see that here with, basically this wave. You can calculate, again, you break it into parts, you integrate it, you define essentially your period. In this instance, my period is 3. So again, fundamental frequency, delta F is over 1 over T. Number of harmonics times delta F, that's equal to F max. So for your largest value of N. And then you're going to calculate and get your frequency spectrum. We can see here, once again, this is our dominant frequency. And then you can approximate, and you can see this is a really nice, kind of approximation here. So this is fantastic. And there's lots of scenarios we're going to do continuous Fourier transforms. However, I will say most of you all, unless you're going to be deep into theory and doing other things, are really not going to use continuous Fourier transforms a lot. Instead, you're going to be using the topic of our next lecture, where we're going to get into discrete Fourier transforms and signal aliasing and spectral leakage, and which is really, really, really important. Basically dealing with non-continuous functions. So how do we deal with, when you have raw data? And how do we apply Fourier transforms to that? So we'll see you then on the next video. Thanks. Bye.